All right. Thanks, guys. Thanks, guys. Thank you. Oh, man, every day. All right, here we go. So what we did before was we estimated a population proportion, right? And so our formula for estimating a population proportion was this lovely guy right here. Divided by n. Okay? So basically we have the statistic, right? Plus or minus the critical value, which in this case was a z-score, times the standard deviation, but really we did the standard error because we replaced p with p hat, right? So what do you guys think the formula is going to be for population mean? Instead of p hat, what do you think we're going to use? X bar. Mu would be the true mean, right? Which is what we're trying to estimate. Plus or minus, possibly the z-score, but we'll talk about that, times the standard deviation. What's the formula that we learned for the standard deviation of mean? Do you guys remember it? There was a square root of n involved, yes. Yes. Okay, it looks like this. So we have sigma divided by n. Now, sigma is actually the population standard deviation, and you should make note of that. You want to be able to identify the difference. Okay, so sigma is the population standard deviation. So when we did our lovely calculator activity, the mystery mean, right? You guys remember that? We actually did know the population standard deviation. Okay, we knew that. So if you know that, you can use this formula, and only if you know this, population standard deviation. How many times do you think we're going to actually know the population standard deviation? Not a lot, right? If we don't know the actual population mean, mu, why would we know sigma? Okay? It's probably not going to happen. Now, the mystery mean activity, we did. So in that case, you can use this formula, and it's called a one sample z interval for a population mean. I would write that down just in case. All right? We used proportion last time. Yeah. Very similar, though. Very similar. So write that formula down and what it's called. I should have put it in the same thing. Here, I'll write it right here. Z-score. It's a critical value. Yep, just the Z-score. Okay, so since we typically don't know sigma, which is the population standard deviation, what do you think we're going to use? Well, we knew 20 in that one. We would use 20 in that one. Good, good. But what did we do last time we replaced P, guys, with P hat, right? Which was our sample proportion. So instead of using our population standard deviation, we're going to use our sample standard deviation, right? So this is called the standard error, just like we called it when we did proportions. And instead of the sigma, we use Sx. Okay, what's the Sx mean? It is our sample standard deviation. You will be putting data into your calculator on some of these and doing that one variable statistics where it gives you X bar. It also gives you Sx, so you need to know the difference between Sx and sigma, okay? So you're looking for Sx. We're also going to be using what's called a t distribution instead of a z distribution, all right? So the t distribution has a table in the back of the book, just like the z does. You can also do an inverse t, just like you did inverse norm for the z, all right? The only difference is you have to use n minus 1. It's called degrees of freedom. It still has to do with your population size. So if your population, you like have 8 people or something, and you like we're looking at their heart rate or whatever, 8 people, you're going to use 7 when we look at the table, all right? If you sampled 10 people, you're going to use 9. That's it, n minus 1, all right? So t distribution is always n minus 1. Now, there was a whole activity in the book where you go through why the z distribution doesn't work, all right? I felt like it was going to take a long time, so just know it doesn't work, all right? It captures not enough area, all right? The z distribution for means doesn't work. What? We're not going to. We're going to change the formula to T star. Watch the magic. Because when can you use that formula? If they give you all that stuff, yeah, you can use that formula if they give you the standard deviation of the population. That's why I wrote it down for you. All right? So anyways, here's the differences, and you guys should make note of these. So there is a t distribution for every positive degrees of freedom. All t distributions are unimodal, symmetric, and centered at 0. It actually looks really similar to the normal curve. And the t distributions approach the standard normal distribution as the number of degrees of freedom increases, meaning as your sample size increases. It gets closer to the normal distribution, all right? But we're going to have a lot more accuracy using the t statistic. So our normal curve actually goes a little higher, and our t curve has more width on the ends but goes lower. Looks really good right there. This is our t curve. So there's the formula you guys were looking for. Oh, this should be x bar. All right, and just so you can visualize the formulas, I don't know that you're going to need to know, except for some of the multiple choice tests did this last time. If we're doing a z-score, our general formula for a z-score was the data point minus the mean divided by the standard deviation, right? So the t-score looks really similar, data point minus the mean, divided by this right here, our standard deviation of our sample. All right, but we're going to find all of our t-scores using table B in the back or your calculator. Table B is actually pretty easy, so we are going to do that first. It is not. There's a whole nother yellow sheet, so I'm pretty sure you're going to get it on the AP exam, which is great, but there's a whole nother yellow sheet with the t-table on it. But flip to the back of the book, you guys, and find table B, and it should have t-scores. Looks a little bit like that. A lot like that. Probably exactly like that. Everybody find it? All right, so let's say we want a 95% confidence interval based on an SRS of size 12. First thing you always want to state is your degrees of freedom. So if my sample size is 12, DF, degrees of freedom, is 11. All right, it's always one less. For our 95% confidence, this is the same thing we did with the z-scores. You take the 5% and divide by 2 because you're finding the point on the graph, okay? So 5% is 0.05 divided by 2. We want to find 0.025. Okay, 5% divided by 2 since it's equal on both sides. So we've got our lovely picture. So 0.025 is right here. Okay, there's 0.025. And degrees of freedom, 11. So we want to find the number that correlates Hopefully I did that right, and we can see. Do you guys get 2.201? All right, so my t-score, t-star, is 2.201. Okay. Let's say for part B, we want a 90% confidence interval from a random sample of 48 observations. So 90%, we do 10%, which is 0.1, and divide by 2. So what are we going to use for our decimal for 90%? 0.05, okay? And our degrees of freedom is one less than our number of observations, so 47 in this case. And so we go to our chart, and we look for 0.05, which is here. And notice that they don't exactly have 47, right? We can use our calculator, yes. What you always want to do is round down. If you round up, you're getting actually a more accurate estimate. Remember, the bigger the sample, right, the better. So to be conservative, you always round down when you're using the table. On your calculator, you don't have to. You can be exact, all right? So I'm going to round down, and I'm actually going to use degrees of freedom 40. So 40 with 0.05. Hard to see. Is that 40? I think it is. Oh, shoot. I lost my 0.05 at the top. Is it this one?
Yeah, that's it.
Oh, that's so nice. It gives you 90% down there. Thanks, guys. 1.678 is what it should be. I got off somehow. Did you guys get 1.678? No?
1.684.
Oh. I believe you. I must be looking at my calculator one, probably. All right. So there's from table B. Okay, now let's try it on our calculators. So you guys might want to write this down first in your notes, just in case you forget. You go statistics, distribution, inverse t, and all you're plugging in is that area decimal and your degrees of freedom. So 1 minus and minus 1. So let's try it. Menu, maybe. All right, menu, statistics, and distributions, and notice inverse t. All right, inverse t. So anytime we're doing sample means, all right, inverse t. So we'll do the first one, which was 95% confidence, so 0.025. And our degrees of freedom was 11 on the first one. Okay. Notice it's negative. Okay, we don't care that it's negative because they're on both sides. We're doing plus and minus, so always plug it in as just 2.201. All right, and then same thing on the other one, you guys. Do you need me to show you? Plug in 47, though, and so it'll be slightly more accurate than table B. Any questions on t-scores? Good. Yeah, I don't know. All right, you guys try this one. A 96% confidence interval based on a random sample of 22 observations. You can use your calculator if you want, or table B. All right, so 96%, you guys, what decimal should you plug in for your area? 0.02. Right, 4% divided by 2. 0.02. And what degrees of freedom are you guys using? 21. So hopefully you got 2.189. I feel like we don't need to do another one, right? Just be careful on the 99%. What decimal do you plug in? 0.005. right? Don't forget that. Okay, so we of course have conditions for estimating mu, which are really similar to our conditions for estimating p. Okay. We still have to have a random sample. We still have to have the 10% condition, which is this, right? Again, if you're sampling with replacement, then you don't have to check the 10% condition, but most of the time we're not, okay? And then we check normality, which is different for x bar, right? When we check normality for p, we do n times p greater than or equal to 10, and n times 1 minus p greater than or equal to 10. What's the magic number when we're estimating mu? 30. Good. So we want to check greater than or equal to 30. When do we not have to check that? Remember there was one. Yes, if the population is normal and they tell you that, then you can just say, all right, we're good to go. We have normality. So you can either have the population's normal, or you can have large counts greater than or equal to 30. There's one other way that we are going to add normality. If you have a small sample, okay, so if your sample size is under 30, you actually need to look at the graph of the data. Check graph. So maybe they give you 8 numbers for something, right? We have to look at the graph because it's not bigger than 30. We don't know the population's normal. Then graph it. So there's a few graphs you can look at. You can use your calculator. So you could do a histogram. You could do a box plot. And anybody remember the name of this? Normal probability plot is helpful. If it's linear, that means it's normal, okay? So any of those graphs would support it. You could say roughly symmetric, and this one's roughly linear. So all of these would be good to go if you have a small sample and you're looking at the graph, all right? So let's look at some graphs that maybe won't be perfect and when you can use it or not use it. Okay, if you've got a really long whisker, we've got some points out here that's pulling the graph. This is skewed what? This is skewed right. These high numbers are pulling the graph to the right. So this would be called skewed right. Okay? And this one's fairly normal. This one would be good to go. Yay. We could still progress with the problem. Or maybe I should put sad face, because you'd probably be happy if you can't, right? And anytime there are outliers, it's a no-go. All right? If you have outliers, do not calculate any kind of t-score. All right? And this is what it says about skewed. Okay? If it is strongly skewed, it's a no-go. If it's moderately skewed, you can still go for it. All right? Yeah, use your judgment. All right? So let's see if I wrote this down. To be safe, you should only use a t-distribution for small samples. Again, this is only when you have small samples. You have to do this. You can only do it if there's no outliers and there's no strong skewness. All right? No outliers or strong skewness. Strong is going to be, it's going to be hard. I don't know. All right? Moderately strong, you can still do it. All right? Keep proceeding with the problem. At least outliers is more black and white, right? If you have an outlier, no go. It's a no go, all right? So let's look at some examples. Determine if we can safely use a t-star critical value to calculate a confidence interval for the population mean. Part A. So A goes with the A graph there on the left, you guys. So this one says, to estimate the average GPA of students at your school, you randomly select 50 students from classes you take. Is a histogram, figure A is a histogram of their GPAs. Now, figure A actually looks pretty good. You could say that's roughly symmetric. However, there's a problem with how they sampled, which is what we've talked about before. What's the problem with how they sampled on A? Yeah, It's not really a random sample if you're going to do it that way. All right? So A is no because it's not random, even though you have a symmetric graph. All right? Part B, how much force does it take to pull wood apart? So figure B, that's this guy right here, shows a stem plot of the force in pounds required to pull apart a random sample of 20 pieces of Douglas fir. Look at this guy right here, right? We've got this stem and leaf. What is happening? It is strongly skewed left because of all these low numbers. So, nope. All right? You would say strongly skewed left because there's a whole bunch of low numbers. Look at all those low numbers.
I know, so that's why it's moderate. Like,
what? More low numbers would be strong.
What happened?
And those could possibly be outliers as well. All right? So no. Part C, suppose you want to estimate the mean SAT math score at a large high school. Figure C is a box plot of the SAT math scores for a random sample of 20 students. So we did do a random sample. So this one, the book says, and if you guys say it's strongly skewed and say no, I guess that's fine, but the book says on this one it is moderately skewed with no outliers, so you're good to go. This one is a good news. You can do the whole problem.
Wait, so if you guys don't want to do a problem?
I know, right? Pretty sure. All right, if a question on the AP exam asks you to calculate a confidence interval, all the conditions should be met. However, you are still required to state the conditions and show evidence that they are met. So make sure you are showing that you have the evidence that the conditions are met. Hopefully the ones on the AP exam will not be questionable. That would be my hope. I don't know. Okay?